last time? Last time we got to the Eisenstein series. We were looking at the hyperbolic Laplacian. We found a nice, yeah, well, that's okay. We saw that the imaginary part of z to the s is an eigenfunction, that it will still be an eigenfunction when we put any element of g in there. But now we want to make something that's gamma invariant. Gamma, of course, is SL2z.
And gamma 0.
And this is invariant under translation, so we better mod out by, yeah, gamma infinity.
Oh, yeah.
I knew what you meant. Okay, and this was our Eisenstein series. Then we observed that if we take this Eisenstein series and we evaluate it at alpha q, so q is a quadratic form A, B, C, and alpha q is negative b plus. The discriminant is imaginary. D equals b squared minus 4 AC is negative. So if we evaluate it, bless you, at this point, then we get, so what do we get? So it's this sum. The imaginary part is, well, let me put it here. It's a sum over bottom rows, C and D coprime. And then the imaginary part of Z to the S, the imaginary part of this is root D over 2A to the S. I'm just reminding you of the calculation. And then 1 over norm CZ plus D, where Z is alpha Q. And this is what we saw came out to be 1 over A times Q of C negative D, something like this.
Incredible.
All to the S. Okay, the A's canceled. And then we got something like this. Yeah, exactly. So the root D over 2 to the S pulls out. And then we just get this, which I can drop the minus sign. So we get this Epstein zeta function.
And are they like called Epstein because he studied them, or is this
I mean, Dirichlet studied these. So I don't actually know the history of why Epstein's name is attached to this. I don't know, Lewis, if you know.
Did something special with it?
I'm
Yeah,
not sure either.
Say it again, Lewis.
I just said I didn't know.
Yeah, okay. I mean, it's something you can do for any quadratic form. You can take the Dirichlet series, which is what values it represents. Is that as far as we got? Oh, and then we did one more thing. We observed that if you, I claimed, okay, so we're working our way towards the class number.
Yes.
Okay, so now let's really get there. So if we let X sub D be the set of all quadratic forms A, B, C with discriminant D, D is fixed, and A, B, C are coprime. So this is all quadratic forms. There's an action of SL2Z on these quadratic forms, which is just the replacing Q by Q composed of gamma.
Right. Change of variables.
Change of variables, yep, invertible, so proper equivalence. And the class group CD is exactly this set XD modulo gamma. We also observed, since the Eisenstein series is a function on H mod gamma, it's gamma invariant in the Z variable. This is a complex number, and as defined, this only converges if the real part of S is bigger than 1. So if we sum, and so the point is, if Q and Q prime, if Q is equivalent to some Q prime, then the Eisenstein series takes the same values at alpha Q as at alpha Q prime. So far, so good. Okay. So, so this is the class group. the number of elements here is the class number. H of D is the size of the class group. I still haven't given it, it's still a class set for us. I haven't given it a group structure, but Gauss did.
In the reading seminar, we're also a class group, and it's still like, don't know much about it.
Okay, so I'll make a note to self to give you the group structure. It's actually very, I mean, it's very beautiful. So here's what we want to do. We want to look at the following thing. If we sum over forms, classes in the class group of E of alpha, well, it doesn't matter which one we take. The whole class has the same value, S. Okay. So by this calculation, this is a sum. So I get this factor root D over 2 to the S. They all have the same discriminant D. So this factor is common to all of them.
Class number.
And then, well, there's a different contribution for each one. At least at first. What we're going to do is take the residue. We're gonna show that there's an analytic continuation and there's a constant residue. It doesn't depend on this value. That's how we're gonna get the class number.
Wait, what did we say this? Oh, because right, we're taking inequivalent.
Yes.
I'm being very silly. Yeah, you said for equivalent ones, right, you're gonna get the same contribution. But here we're just, yeah, we're looking at the different ones, right?
Okay, but now I want to say, let's take quadratic forms. CD is XD mod gamma. This is an XD mod gamma. And then what was this? This is a sum over, how do I get these bottom rows CD? Well, it's gamma in gamma mod gamma infinity of 1 over Q. How do I get CD out of the quadratic form? Out of a matrix gamma, gamma is ABCD. How do I get the bottom row out of it? I take gamma and I multiply by the thing that picks off the bottom row. So tell me if you agree with this. I'm trying to find a way to show everything at once. So if we look at the sum over all of the forms in the class group, there's a finite sum. We showed that the class number is finite of the Eisenstein series evaluated at these different heat nerve points. There's a common factor to all of them that pulls out. And then there's, again, this is just the same thing, the same way of writing the same thing, sum over forms up to equivalence, and then a sum over C's and D's. This was a sum over gamma mod gamma infinity. The C's and D's are exactly the bottom rows.
Okay, so you just, yeah, rewriting.
I'm just rewriting this in this way.
0, 1, gamma.
I'm just saying that 0, 1 times ABCD
Just like with the
is,
fractional sort of action.
well, this is just me. This is just, you know, a 2 by a 1 by 2 times just literally the linear action. Yeah. Picks off CD.
Yeah.
Okay. And now look at what we have.
It's like an unfolding.
This is an unfolding argument. Okay, so if we unfold this double sum, we have a sum over all quadratic forms, not up to, well, a sum over all quadratic forms up to equivalence, and then a sum over the equivalent ones up to gamma infinity. Okay, so if we unfold this,
XB gamma infinity. I always have issues understanding why we can unfold.
so
Yes, but
so in every XD, we can make a choice of gamma.
right, so
We can take the primitive one, for example. And then this says, take that Q and move it by gamma, but up to, move it by some gamma, but it doesn't matter what the numerators were.
okay.
Well, isn't that the same as summing over just all forms except up to translation by gamma infinity of 1 over q just of 0, 1. Yes.
So are we saying it's sort of like in bijection? Is what we're
Yeah.
saying? Like we're just, okay, so you take a Q.
Yeah. So if we take the q's up to equivalence, but then we translate them by gammas by exactly the same equivalence up to this gamma infinity and evaluate it at q composed with gamma, which is what the equivalence was in the first place. So I'm canceling the gamma down here and up here.
Still kind of confusing that, but
Okay, so let's see, what's the better way of explaining this?
I guess yeah, like how, I'm not understanding well how Q is getting affected by both of these things.
Okay, so we have XD. XD is here. We have lots of quadratic forms,
Okay, those
infinitely
are
many,
just your quadratic forms. Yeah.
right? And then we have the projection to XD mod gamma. So now we have just finitely many forms,
You
and
group them
everybody,
together, like-
everybody's getting grouped.
Okay,
Now, in each group, I'm going to sum over the different ways of moving it around, but up to a different grouping. So there's another grouping, a sort of a smaller grouping. In between this is the quotient. So this is the quotient x mod all of gamma. Let's see, can I zoom in here? There's also x mod gamma infinity. So you can group them by gamma infinity, or you can group, sorry?
XD or something?
XD mod gamma infinity. So XD mod gamma infinity is I only group them not up to all matrices, but only up to translations.
Right. And then your groups are gonna be.
Well, there the groups will be infinite in size,
Yeah,
potentially. And then we can group them just by gammas. So what I'm saying is, if you're summing only over these groupings, and then you sum over the quotient gamma mod gamma infinity, that's the same as only grouping them by gamma infinities and summing over this set. Take a minute and think about it. You'll see that that's exactly what's going on.
yeah, I guess like this is like not even that bad in the sense that the left sum is finite even.
This sum is finite. This sum, of course, is infinite. And so this whole sum is infinite.
Right. Right, and then you're just saying that it's the same as grouping them by their gamma infinity.
Exactly.
Cosets.
Exactly. I mean, do you agree that if I took x of d mod gamma and then summed over all gamma of q composed with gamma, that would just be summing over all xd's? So I take all quadratic forms and mod out by xd, and then I sum over all xd's of the
Over all gammas. you mean-
over all gammas.
Yeah, then you recover everything.
Then I
back.
just recover the original set.
Okay,
So now I'm not summing over all gammas. I'm only summing over cosets, gamma infinity cosets of gammas.
oh, I see, so you're recovering,
So I'm recovering gamma infinity cosets of xd's.
oh, okay, I think that.
But let's make this even more explicit. So
Yeah, I'm just asking more because later on there are the more delicate unfoldings and then like,
we'll see some more unfoldings. Yeah.
like
So-
the whole, like for the holomorphic Eisenstein.
Right.
Okay.
So if Q is ABC, what's Q of 0, 1?
0, 1, and that's gonna give you.
A times 0
last-
squared.
yeah,
It's just
last
C.
one. Yeah,
It's just C. Okay. Now, what happens to different quadratic forms? So if I have Q of what happens to the coefficients of Q when I move it by an element of gamma infinity? When I move it by, 1L01 or something. So the original Q was ax squared plus bx plus c. And now I want to understand what is the set of Q up to this equivalence. Because XD is just all possible quadratic, all A, B's, and C's with B squared minus 4AC equal to D, that fixed number.
now we're gonna see what are we calling equivalent. Right?
Exactly. Exactly. So what's the equivalence? So if you multiply this out, you get what? X and Lx plus y.
Yes.
Okay, so any of these are equivalent to the original Q under gamma infinity.
So your first coordinate doesn't change.
Well, exactly. So let's put it into what the quadratic form does. It takes a times x squared, and then it does b times x times y, which is now Lx plus y. And then it does c times y squared, Lx plus y squared. So what are the new coefficients? The new coefficients, what's the coefficient of x squared? I have an a.
It's gonna be a plus bl
bl
plus l squared.
plus cl squared.
CL squared.
Okay, so this is the new x squared coefficient. It's a good thing I don't care about the x squared coefficient. I'll only care about the c coefficient. What's the new b coefficient? What's the new cross term? There's a bxy.
And then there is a 2 CL
xy. And then what about a y squared? There's no y squareds here or here. It's just a c y squared.
So when you're doing Q of 0, 1.
So they have the same c, of course. That's why we can pick. That's why this sum is well defined. This is picking off the c term, which only depends on xd mod gamma infinity. But let's understand what this set is. So if we take the set of all things, this is the set of all triplets A, B, C co-prime with b squared minus 4ac equal to d. This is in quadratic. This is all integer points with this. But now I can change b. So c I can't do anything with. Once b and c are determined, a is of course determined. But b I can move by 2c, by any multiple of 2c. In other words, b is in z mod 2c. So once I choose any, so I can choose c's freely. For any choice of c, I have 2c possible values of b, with the restriction that the only b's that can arise are ones for which there's a solution to this equation.
Right. And that would determine your A already, so you don't have to worry about that.
Exactly, and that determines a.
That,
Okay, so let's write this sum in a different way.
but not all those B's are options, are they?
Not all of those b's are options. Yeah, only the only the ones with this property. Exactly. And so let's. Yep. So if I write this whole thing, as these are just some integers, right? Some c's to a power. So if I write this as a sum over all c's, c to the s, times r of c, which is the number of representations of c, the number of times c occurs. So given c, where, in other words, I'm grading this xd mod gamma infinity by this c's, where r of c is the number of b's mod 2c, such that there exists an a with b squared minus 4ac equal to d.
Solutions B.
The number of solutions b to this equation.
That specific C.
Right.
Okay.
And those b's only need to range mod 2c because we're modding out by gamma infinity, and gamma infinity changes b by multiples of 2c. So by moving it under gamma infinity and in that equivalence class, I can choose a representative so that b is between 0 and 2c minus 1 or something. But it doesn't matter which representative we take. Okay. What does it mean? So let's see. Do I want to take the time to do this? Where's my clock? Here's my clock. Because I want to get to the Well, let me give you a hint as to how to do this. So by the way, there exists such an A. How do we tell if there's such an A or not? So there exists such an A if and only if B squared is congruent to D mod for C.
This is just a, Legendre.
It's just the Legendre symbol. Exactly. So
Just a character, right?
it's just a character. Exactly. If there exists such an, so for how many B's, we want to know for how many B's mod 2C is the Legendre symbol, is D a square mod?
And 4 shouldn't affect anything, right? Because 4 itself is already good.
Right, and D is, if you recall, negative Q, where Q is 3 mod 4. This is the setting of the original. If we go all the way back to what we were trying to do with the Dirichlet character L1 chi is the real character mod Q.
And then C, I guess C then it depends.
Well, C runs over all integers, and you have this thing here. So we're very close to. Let me leave the rest of it as an exercise to show that R of C is actually the sum over divisors of C. Can I use L? L dividing C of this character, chi of L. And one way to see that is to break this. You have an equation here that you're trying to solve. You can break it into prime powers. If C is a prime, then this is exactly 1 plus chi of that power. Does that make sense? Should I say that more slowly?
Say it one more time.
Yeah. So, for example, if C is itself a prime, and let's forget about the 2's, then the number of B mod C, so that B squared, the number of solutions to
2 or 0, right?
is either 2 or 0. This is just 1 plus chi of P or C, chi of P.
Right, because the chi is going to be either -1 if it's 0 if you have no solutions, or it's going to be 1 if you do have solutions.
Exactly.
Chi is the real character mod.
Chi is the character mod Q, where Q is negative D. And do you need quadratic reciprocity here? So D is 1 mod 4. So quadratic reciprocity is anyway
If you're a prime, you're fine, because like the 4 contributes to nothing because it's already a square.
about a square.
So then you're dealing mod of prime, so this
Yeah.
is literally just the,
But chi of P is the real character.
That's right.
yes.
So it's plus or minus 1 or 0. Yeah.
Okay.
And so when you take the product over all those primes dividing C, that you can expand and you just get a divisor sum. You get 1 plus chi is this, what am I saying? If you have the product over primes dividing C of 1 plus chi of P, that's the same as the sum over all possible divisors, right? When you multiply all this out of chi of L.
Exercise.
Well, exercise, and then I do most of the exercise for you. I mean, there's some details to fill in, but this is basically the thing. Okay, so let's, sorry.
No, I'm good.
Okay.
Yeah.
So we're almost there. So what have we got? We've got the sum over forms in the class group E of alpha Q of S on one hand. On the other hand, we have this root D over 2 to the S, a sum over C, 1 over C to the S, and then this however many representations there are, but we know how many representations there are. The number of representations is a sum over L dividing C of chi of L.
Which we just did by looking at what this action is a lot more closely.
Exactly. But what is this? This is the Dirichlet convolution of 1 and chi of C. Well, when you make a Dirichlet series out of a Dirichlet convolution,
Yeah.
this is just the product of the corresponding Dirichlet series, which is zeta times chi.
Oh, yeah.
Very nice.
Okay, so now there's an even better way, perhaps. I shouldn't take another detour. There's an even better way to recognize. Here I go taking a detour. There's an even better way of the scenic route. I keep promising the scenic route. Well, I guess I'm delivering in some sense. There's an even better way to recognize this, which is as the Dedekind zeta function of this quadratic extension, k being the field q adjoint root d, which is this negative quadratic field.
Right, and how is, wait, are you saying you define it as this, or?
Well, let's take a few minutes and talk about it.
Okay.
Why not?
I'm just curious, what exactly
This means. Okay, so we have this imaginary quadratic field. This is imaginary quadratic, although what I'm going to say is applies in general. So we're doing a little bit of algebraic number theory. Okay, what's the ring of integers? Ring of integers of k.
1 plus.
Yeah, so what does this even mean?
That's about the line polynomial.
Exactly. So recall,
Or in Z, sorry.
yeah, so alpha is an algebraic number if there exists a polynomial with coefficients in z, so that alpha is a root of that thing, and alpha is an algebraic integer if this polynomial, if there exists a monic polynomial. Okay, so what's the ring of integers? Well, you might think that it should be just z adjoint root d,
Some extra stuff.
but there is an extra thing because there's a polynomial. So this polynomial, x squared minus x minus, remember, in our case, d is 1 mod 4.
Right, so you can take d minus 1/4.
Exactly, minus d minus 1/4 minus 1/4. This is an integer valued polynomial. Its discriminant is b squared minus, so b squared minus 4ac is exactly d. It's discriminant d. And so the root of this polynomial, which is 1 plus root d minus 1
That's
over.
number 2, because
So the root of this polynomial is an algebraic integer defined over this ring,
yeah.
this number field.
And this key here, right, the b is like not divisible by 2, because if it were, then you could actually cancel the 2 out.
Well, I still get a root d over 2. You're saying I could cancel if b had to be
Oh,
even?
yeah, no, you're.
Okay.
Yeah, the d is 1 mod 4, so you wouldn't be able to cancel anything. Yeah, I see what you mean.
So it turns out that the ring of integers, so this is an order. This is an order, a subring of, of the same rank. But the full ring of integers is z adjoin 1 plus root d over 2. So as a lattice, if we're thinking about these as points in C, we have all the integers, 0, 1, 2, 3, -1, and so on. And then we have this funny number, a half plus root d. So a half plus root d is over here. And then, of course, twice that will be over here. So we have this, lattice. Whereas this order is just the order that contains these points.
Is there a nice argument that tells us that if we have an extension, a finite extension over Q, then the ring of integers would be, in some sense, like discrete?
Anyway, you have to build up the theory. That's what we're doing in the algebraic number
I guess
theory.
that's all.
Yeah.
I'm not sure.
And it's sort of like
Why'd you put the other points imaginary?
because of these negative.
D is negative.
Oh, right, okay. Of course.
Yeah,
But
so we have an
that's
imaginary
sort of the
quadratic field.
foundation
Yeah,
of
yeah.
the-
Yeah.
You slowly go through it, or
Yeah, this is just a crash course in, you know.
fascinating.
Okay, I'll ask Josh.
So then we have ideals. We have integral ideals in the ring of integers, an ideal. So an ideal, you know what an ideal is, for all A in A and X in O, XA is in the ideal. And the Dedekind, so Dedekind realized that the way to make a zeta function for any ring is to sum over all ideals, not the zero ideal, 1 over the norm of the ideal. So what's the norm?
Here you mean specifically integral ideals,
Integral ideals,
not the fractional.
right? Integral ideals. 1 over the norm. So the norm. So this ideal, what does it mean to be an ideal? It means that the quotient is just some finite group. So the size of this is.
I guess
is the
here
norm.
you're sort of using, right, that in a Dedekind domain, your prime ideals are maximal, right?
Right.
And so you're going to get a finite field out of this.
Well, it's not a field unless alpha is prime.
Oh, wait, but you're,
This is just all
oh,
alpha.
you're just taking all ideals in
Yeah.
general. Okay.
But ideals decompose into prime ideals.
Yeah.
And so we have by the same, this is exactly why Dedekind, I think, wanted to look at this, is because you get exactly the same Euler product formula, but now on the level of prime ideals of 1 minus 1 over the norm of this prime ideal to the S power inverse.
Because you have this factorization.
Because of the unique factorization of ideals into prime ideals.
We haven't gotten this far, but this is makes sense.
Okay, and so what is the norm? So this depends on whether P splits or not. So the norms are all, so what could happen? What could happen?
Norms are multiplicative, right?
The norms are multiplicative. The prime, so if you have a prime P, a rational prime P is a rational prime. In other words, a prime over Q. Then in K, it might split or it might not. It might be inert. Okay, and it could be ramified, but never mind. It could split. So P, the ideal generated by P, could split into P times P bar, or it could already be inert. Or this could already be a prime ideal. Okay. In this case, the norm of P is exactly P. And there's 2 of them. I'm just,
So we,
what are you looking at? What are you confused by?
anyway, so you're taking P to be the ideal generated by the element.
Yes,
The
by this
principal ideal
rational,
generated by P.
yes,
And then you are saying, okay, say we can decompose that.
right?
Then what I'm thinking is you should be able to apply the norm on,
Yes, and
Both
so, and
sides.
the norm of this is P squared.
yes, yeah.
And so the norms of each of these must be P.
Oh, that's what you're saying. Okay, okay.
So the norms of each of these are P, but the norm of the inert ones is P squared. The norm of the ideal generated by P is P squared. And so depend now which primes split and which ones don't. It depends on D, but it's exactly the Legendre symbol that determines which primes split and not. So this product over primes,
Right, This is going to give you a quadratic of some sort, right? Like you have, these are real numbers. In order to,
yeah, you'll see in a second. So let's say it's a product over P's that split. If they split into 2 factors. Each of the factors has norm just P. So this is 1 over P to the S squared.
if they split.
And then the ones that are inert, P inert, you get 1 minus 1 over just P squared to the S inverse. If the rational prime splits, then you get 2 copies, then you get P and P bar. Each of them contribute 1 minus, the norm is just a rational number. The norm is just P. So you get this for one of them and you get this for the other one. If the prime remains inert,
Your norm is,
then the norm is just p squared.
okay.
And so now it's p squared to the s, and there's just one factor.
And then it's, because we have a degree 2 extension, it's always true that if you have a prime ideal, which is not given by, generated by a rational prime, it times its conjugate, so that product of those prime ideals will be one is a prime ideal of that, or sorry, an ideal of that form.
Exactly.
Okay.
Yep.
And that does depend on the fact that we're in degree 2 extension.
Well, in general, it'd be the product over all of the, if you have lots of different embeddings,
Right.
the product over all the embeddings.
Okay, and then we have 2. Okay.
Yeah. There's two embeddings.
Yeah,
Yeah.
that all makes sense.
Right. So if we have like, there's this Galois sort of representation of the norm function, right?
Yep.
And then you can, it's a product and it traces a sum over these
Yeah.
embeddings, right?
Yep. So check this out. We have a difference of squares. This is 1 minus 1 over p to the s inverse times 1 minus 1 plus 1 over p to the s inverse, which let me write as 1 minus negative 1 over p to the s inverse. So we get one factor either way. So we get a product over all primes, and we get one factor either way. And then let's write a product over all primes. But now we either get a +1 or a -1, depending on what p is. That's exactly what the character picks off.
Given that, right, this is conditional on what? That the.
You mean the
whether they
splitting
factor-
structure?
Whether they factor or not depends on the character itself.
Exactly.
Given that piece of information, then.
Right.
We can do this.
Whether it's a square or not is exactly what determines whether or not this factors.
Right. Okay.
Okay, well, what is this? This is zeta. It's the same formula. LS. Okay, so this is sort of,
And we have, even though we're doing this over ideals and whatnot, with this norm function, we don't have any convergence issues. Because norm takes you to the integers.
yeah,
As we would normally.
yeah, if this converges if real part of S is bigger than 1,
Oh,
same as,
But I guess it's like. I'm wondering, what if you get like a bunch of copies of same norm? I guess.
there's a calculation to the size of the, how many ideals are there in a ball and so on.
Yeah, and then use that for convergence, and you're saying that you get
Yeah,
sigma greater than
1, yeah.
Well, that's very cool.
Okay, so the point is there's a modern viewpoint on these things, which doesn't go through quadratic forms, but has exactly the same consequence. It goes through ideals, and then realizes this thing that we're getting on the other side is this Dedekind. I didn't write it. Dedekind Zeta function.
And the way we did it in the right-hand side was probably how it's first developed, and then people
Yes.
interpret it as the left-hand side afterwards.
That's right. That's
Okay.
right. Dedekind is much later than well. Okay, so Dirichlet wasn't doing this either. I'm going all over the place time chronologically in terms of chronology, but
Scenic route.
scenic route. That's right. So what we so to summary. So far, we've shown that if you sum quadratic forms up to equivalence over the class group, E of alpha Q S. Now something's a little funny, and I don't know where I lost a factor of zeta of 2. Lewis, I don't know if you see where it went, but these should be E stars actually.
Yeah, because we've been writing E instead of E star.
Right.
It's like,
So there's a factor of zeta of 2s that should be in here.
Oh,
to
yes,
make
that
this
was
an E
because
star.
from one representation of E to the other
every time
one,
that it's E star.
then you have the zeta.
Exactly.
Yeah.
And
You wrote these as strictly equal when really one has a zeta and the other one doesn't.
yeah, I just need to put a star on E's.
Okay.
Yes.
Um,
Let me just finish writing this and then so the point is there's a zeta times an L. Okay, what's the question? Okay.
so why do we call, okay, which one's the non-homomorphic one, E or E star?
They're both non-holomorphic.
Okay.
You have like the
One is-
value.
One is a sum
Why do
over
we call
co-prime.
one of them non-homomorphic one?
say it again.
Why do we call one of them the non-holomorphic?
We called
There is
either
a
of them the
holomorphic.
non-holomorphic one.
Okay,
The original Eisenstein series, the way it's defined here, to make it patently a sum over gamma mod gamma infinity, so that it's obviously gamma invariant, means that there's co-primes. C and D are co-prime. And then if you want to free C and D to be to range over all n and m, then there's just a factor of zeta of 2s.
yeah, I remember that. I thought maybe like one of those was the holomorphic Eisenstein series and one was not, but then somehow we'll find that Zeta of 2s with this holomorphic was.
Was going to change it. It doesn't change
That
it.
was, okay,
Yeah, they're both non-holomorphic.
okay.
Although I think, so it's still holomorphic as a function of S though, right?
Of course, it's a holomorphic function of s. It's not a holomorphic function of z. What we'll see
Right.
later is instead of s, we'll have an even integer k. And instead of z, we'll have, well, we could still have z, but it will be a holomorphic function of z. You'll see.
When we take S
Well,
equals 2K.
Yeah, when we do modular forms.
Yeah, okay, I've seen that. Okay.
Yeah. Okay. So we're very, very close. We observe that the residue of this at s equals 1, there's only one thing that has a pole, which is zeta. The residue of zeta is 1. So I get exactly this factor. L is entire, no poles. So we just get the value. And then we get the value of d over 2 to the 1. So if we could work out what the residue of this thing is, so we need to know that this has a residue. We need to evaluate the residue of this at s equals 1. At the moment, we don't even know that this function extends beyond real part of s bigger
Zeta
than.
to S gives you no issues, right?
Gives me pi squared over 6.
Exactly.
And it turns out that this residue, each one of these, so claim, I'm sort of foreshadowing, each one of these will give me a factor of 3 over pi. Independent of the value of alpha.
And then you have the class number.
And then you'll get the class number.
So
So that's where we'll get a pi. The 3 and the 2 and the 6 all go away. So we get a pi over root d being the class number. Okay, so this is the next step, is the analytic continuation of Eisenstein series.
It's like, I guess, something about this is kind of incredible, right? That we can evaluate zeta of 2s at that value. Like, imagine it been zeta of 3, then it's you'd be carrying this area of 3 around, I guess.
Yeah. Yeah, well, if that's what the value, that's what the L value is, then what can we do about it?
No, we can prove this another way and do that way. It'd be amazing,
Right, right,
Well, then I guess it's true.
because you don't have to do this to prove this.
that's right, that's right. If you had some other way to pick off zeta of 3, you might learn something about zeta of 3. Okay, so continue. So I'd like to do 2 different proofs of the continuation of analytic continuation. So analytic continuation of Eisenstein series. Let's do the one that's in most books. Yeah, which is by Fourier expansion. But then I'm going to see if we have time. We're already a little bit behind from where I was hoping to be, but it's important to be able to do other ones. Okay. So analytic continuation of Eisenstein series. It will be more convenient to analytically continue or to work with that version, which is again zeta of 2s times the other one. If we can continue one, we can continue the other because we've continued zeta already. So again, this is a sum over all integers m and n, not both 0, of y to the s over mz plus n to the 2s. And method 1 will be, so the idea is E star of z plus 1 s is equal to E star of zs, because this is gamma invariant. Gamma includes translation by 1. So z is invariant under translation. So this is a sum over its Fourier series. A sum over, let's see, I have m's and n's, k's, a sum over k in z of whatever the Fourier coefficient is. Let's call that ak.
Which I guess something has to be said about why you can do this pointwise, but the analysis does work out
It's a, yeah, it's a,
All the theorems are,
yeah, it's a smooth function and it has enough decay in some region. So we're gonna see how we can do this. EKX. Okay, so what is this coefficient? AK of Y S. Let's see, should I call this A star so that we remember that there's a zeta that we've put as a, yeah, let's call it A star. I don't know if it'll be annoying to carry that star everywhere, but just to remember that when we go back to the original Eisenstein series, we have to divide by zeta of 2s. Now let's not keep the stars. Okay, what is this? It's the integral, it's the Fourier, the K Fourier transform. So E of x plus Iy s. So it depends on y and s and k, e to the 2 pi I kx dx with a bar. Right? That's just what the K Fourier coefficient is by definition with a star.
0 to 1 is going to find out lattice anyway.
It's invariant under,
Define model lattice.
yeah, it's x goes to x plus 1 is the invariance. I'm integrating over the circle, exactly. Okay, so we have to work out what this is. All right.
Expanded sum, switch, and
There's, yep, this is, you know, sort of hardcore analytic number theory or standard analytic number theory. So there are going to be two terms depending on whether m is 0 or not. So if m equals 0, that means n is anything non-zero. That means there's no z.
you just pick off zeta.
So I just pick off, yeah, so n will range from 1 to infinity. The negative values of n contribute the same as the positive values. And then I get a y to the s over n to the 2s. So I get exactly 2 zeta of 2s y to the s. But of course I get that because the first coefficient of the original Eisenstein series is y to the s. The identity coset contributes y to the s.
Say that to me again?
I multiplied by zeta of 2s
Mhm.
of the original Eisenstein series.
Yeah.
The original Eisenstein series was formed by taking y to the s, moving it by all elements of gamma, mod gamma infinity.
Okay.
What's the identity coset? It's just y to the s itself.
Then the cosine.
In other words, the all the way back here, when gamma is equal to the identity,
Oh.
I just
see.
get y to the s.
What are you picking up?
Yeah, that's the y to the s contribution. So that's the contribution when m is equal to 0. So I shouldn't be surprised to be seeing this factor. So this can only contribute to k equals 0. To the constant term.
We've written the series e to the kx.
In other words, I'm saying that contribution, I'm breaking this up into the contribution from m equals 0 and the contribution from m not equal to 0. The contribution
Oh,
from
so
m equal to
because-
0,
Because we have no exponential, then it has no choice but to be contributing to A0.
there's no x. This is
Right.
independent of x. If
Right,
m
right,
is
right.
0, then the x dies, and anything that doesn't depend on x, it just gets integrated out to 0 unless k is itself 0.
Yeah.
Okay. What about the 2? It's because I'm being fast and loose with summing over SL2Z versus PSL2Z. When I sum over SL2Z, there's the identity component, and then there's the negative identity component. So that's why I'm getting 2 of them, because I'm summing over SL2Z, and really I should be doing it over PSL2Z, or I should be putting a 1/2 here. I'm not going to do either of those things. I'll just leave it as a 2.
Yeah, it is true. I think bump goes ahead and puts the 1/2.
1/2.
So
This is SL2 versus PSL2. Okay, so there's 2 contributions of y to the s.
SL2 versus PSL2 doesn't matter back when we're doing the quadratic form things. Or
Well, no, it doesn't matter because we,
just changing our whole function, but
a factor of 2.
yeah,
I mean, it matters in the end when we want to get the right number that we're seeing for L of 1 chi.
That's
We'll,
what
we'll
I'm
be,
wondering about.
we could be off by a factor of 2 somewhere. Anyway, I don't think we are, but maybe we are. So this needs to be checked for 2s. Hunt down your 2s. That's why I hate PSL versus SL. I just always write SL, and then if I find this factor of 2, then okay, I know where it's coming from. All right. So what about m not equal to 0? If m is not equal to 0, so that will contribute all these other things. Then I can sum over n. I may as well, so you see negative, if I negate both n and m, then I get the same contribution. So can sum,
You get another factor of 2.
I get another factor of 2. And all those factors of 2 would disappear if I was doing PSL. Can sum over m greater than 1 with a factor of 2. With a factor of 2. And then the n sum is completely free. Because m is not equal to 0, n is guaranteed, the pair nm is guaranteed not to be the pair 0, 0. Okay.
And no degeneracy.
And no degeneracy. Okay, so now what does that contribute to a, so for k equal to 0 or not equal to 0, but the m not equal to 0 contribution, this contribution gives this integral from 0 to 1. So E star, what is E star? It's a sum. I mean, this contribution to E star is m bigger than 1. It's a factor of 2. And then a sum over all n and z. Y to the s over cz mn mz plus n squared is an mx plus n squared
Oh, it is expanding.
plus my squared to the s.
Wait, we have norm. Yeah, it used to be to the 2s. Now it's just 3s.
Because I took the norm squared and opened it up knowing what the real part is and what the imaginary part is. Times e to the minus kx dx.
And this is why you're saying it's convenient to have this form, because now.
Now it's a nice big sum. We can really deal with everything. All right, we got some calculations coming. Let's do it. We have a y to the s, independent of x, pulls all the way out. There's a 2y to the s. There's a sum over m bigger than 1. Yeah, everything gets reversed. Yeah, we're in the range of absolute convergence for all of these sums. There's a sum over n. Yeah, let's do it one step at a time. We depending on how comfortable you guys are with these things, we can jump several steps, but let's not do it too fast. Okay, and then I have a 1 over m x plus, so I'm going to do one thing, which is to pull out a factor of m squared to the s. So that's a m to the
You'll
2s.
be able to change variables.
Then I have x plus n over m squared plus y squared to the s, e minus kx dx. So far, so good. I'm going to decompose this. Sorry. It's a little tricky. It's a little tricky. Okay, so let's make a change of variables. X goes to x minus n over m.
And thankfully, exponentials work nicely.
Exactly.
Right, yeah.
Exactly. And I also want to, at the same time, break this up into 2 sums, a sum over n0 mod m, and then a sum over all n that are congruent to n0 mod m. In other words, I just want to break the n sum into progressions depending on its residue class mod m. Okay, so let's do both of those at once. I have a sum of 1 over m to the 2s, a sum over the possible residues, and then a sum over all those n's that lie in that residue mod m. Is it clear what I'm doing here?
The left one, I'm not entirely sure what you mean by that.
Okay, so n runs over all integers z,
Yes.
and then I say group them by their residue class mod m.
and then the other sum means you're picking off each individual one.
No, I'm saying, what are the possible residue classes? This is a finite sum.
Okay, possible residue classes.
So there's a residue class here, there's a residue class here,
Yes.
and then sum over all the things in that residue class. This is a sum over n and z
Oh, I see.
with this condition.
Yeah.
So this is a finite sum, this is an infinite sum.
Progression, as you were saying.
Yep, I'm just breaking the sum over all z into progressions. You'll see in a second why that will work.
Thank you, absolute convergence.
Yes. So we started at 0. Now we need to start at n over m to start at 0. And then we ended at 1. Now we need to end at 1 plus n over m. I have a 1 over, this turns into a nice x squared plus y squared to the s. And now I get an e to the minus k x minus n over m. There's an x minus n over m.
And there you're free.
So what did I do?
Right, yeah. You made this independent. Grab your n0.
Why did I put n0 there? E sub m of x is e of x over m.
Okay.
You just follow the change of variables, right?
I just followed the change of
And then you
variables.
pulled out what was independent of the precise n and what only depended on the.
Bingo.
Yeah.
It wasn't n, it was an e of kn over m. But that n only depends on its residue class mod m, and these all have the same residue class mod m, which means I can pull that sum. So really it went here, and then I can pull it one stage farther by breaking n into progressions, by grouping things by progressions.
Infinite integral?
And now, what is the integral? It's from n over m to 1 plus n over m, summed over things that jump by 1. Because as n jumps to the next residue class, the next entry with the same residue class, mod n, it's moving by m's. And this is exactly going to jump us by 1. So this integral is just an integral over r. And now what we've done is something, I just want to pause here for a second, because this is a very important thing to be able to do in a lot of number theory calculations. I have this, well, in fact, I can do one more thing, which is, what is this sum? It's a complete sum on n0, which either vanishes, or each of these things is equal to 1. So it's m times the indicator function. Why would each of these be equal to 1 if k over m is an integer? In other words, if m divides k. If m divides k, so k over m is an integer, then this sum is 1 every time times m residue classes.
Oh, the red thing doesn't depend on. Oh.
Doesn't depend on n0 or m anymore. Because this sum, the whole thing becomes an integral over r.
Okay, so
N0 and m
So many of
disappear.
those exponential terms. Sure, okay, like we're something over roots, basically.
Uh-huh.
Okay. Okay, sure. So yeah, some of the roots of any set of roots of unity, that's always 0. Unless they're all.
Yep.
Okay. That makes sense.
And now this has completely split
Cool.
into a modular piece and an Archimedean piece.
Modular and Archimedean.
This, why do I call this a modular piece? Because this is actually a finite sum. It's a sum over the divisors of k. This has a name, right? A divisor sum.
Yes.
The only m's that contribute are the ones that divide k. So in other words, it's just the sum over the divisors of k,
Is the divisor?
the divisor function.
Yeah. And
So-
then raised to the, what, 2s minus 1 or something?
Yeah, 1 minus 2s.
1 minus 2s.
So this is sigma 1 minus 2s of k.
Yeah.
Now, k could be positive or negative, but the divisors are just the positive divisors. So it's really sigma of absolute value of k.
Hmm. And the other side is this going to be some sort of,
Let me just note that sigma d of anything, let's call it L, is a sum over m dividing L of m to the s. That's the divisor sum function. This is going to be a little complicated. We have to deal with this.
these, I forgot the name for these.
K-Bessel.
The Bessel functions,
Yeah.
I remember.
Okay. So far, so good. Yeah. This is if this, now I have to be a little bit careful. This is if k is not, this is if k is not equal to 0.
And then you get a zeta contribution for like.
If
this is
k,
the case.
if k is 0,
Yeah.
then this is always m. In other words, there's no restriction. The fact that m divides 0 is not a restriction on m at all.
You'll see the
And I
double
just get-
over, right?
Yep. And this term just becomes zeta of, what is it, 2s minus 1.
This Archimedean piece is gonna be very nice, right, like analytically. But then like the other piece is where you're getting, these zetas are what are giving you poles, right?
Yes, yes. This will not give us poles. Nick, I lost you.
I think I've got it. So just saying that the modular piece is sigma 1 minus 2s of x over k, it's non-zero, and then. Sure, okay.
And if k is 0, then this just is always 1. And so you always get m here. In other words, the condition that m divide k when k is 0 is vacuous. All m divides 0. And so I just get sum of m to the 2s minus 1.
Yep, and that's zeta.
And that's zeta of 2s.
And then in the other case, there's.
Okay?
Yeah.
So now let's deal with the Archimedean part.
0. And you get some sort of gamma function.
So by itself, it's not so easy to evaluate this thing. But there's a trick. The trick is, in order to free the n and the m variables, it was convenient to multiply by zeta of 2s. In order to do the modular, to make the modular part nice, we multiplied by zeta of 2s. To make the Archimedean part nice, we should multiply
Gamma.
by the infinity, by zeta infinity, which is gamma of 2s over 2. Zeta of s comes with a gamma of s over 2 to complete it.
Oh, I see.
So here we needed a zeta of 2s to make the modular part not have a coprimality. It turns out that we multiplied.
Like, how did people even start doing these computations? It feels like so much just works, you know?
You start to get a hunch for what will work and why. We multiplied by zeta of s to clear modular variables.
I love their aesthetic sense, guys. Like, what would be really sweet here?
Yeah,
You would make this really cool. Yeah, we're gonna try that. That's gotta be it.
try multiplying by gamma
Really makes me sense.
Yeah.
of 2s over 2. In other words, just gamma of s, which is almost the infinity factor, the infinite place of zeta.
What's the geometric interpretation of this formula? And that's like, why are we saying, oh, fixes infinity can correspond to the gamma function?
Adelically, they're the same thing. So
Okay.
adelically, the p-adic, the p place of this is just 1 minus 1 over p to the s inverse. That is the analog of the gamma function.
I think we did mention
We-
something like this
yeah.
before, but
Yeah.
I don't know anything about the bells or anything, so.
Maybe we could do a crash course on them too, but let me, since there's a bit of calculating left to do. I want to try to do it in 11 minutes.
Be good to finish the Fourier computation.
Yeah, we should really also stick in a pi to the minus s, and you'll see in a minute that we may as well, that will be a good thing to do. Okay, so we're going to take the Archimedean bit, and we're just going to multiply by gamma.
Then we can turn it into integrals, right? And
Exactly.
together.
Times Archimedean is equal to gamma is an integral from 0 to infinity, e to the minus, I don't know, dummy variable, u to the s, du over u. So I haven't done anything. I'm just taking the gamma function and I'm going to multiply it by this integral over r, 1 over x squared plus y squared to the s.
These feel so heuristic heavy.
Well,
But you know, you're opening it up into integrals, you're putting it, you're gonna do a change of variables, and it's gonna work out magically.
it will work out magically. But I really see multiplying by gamma to make this work out nice, to free the variables as being exactly the same thing as multiplying by zeta to free the c and d that had to be co-primed to make them to be able to sum over all integers instead of worrying about this coprimality condition.
And then these sort of things then come up once and over again in the
Yep.
theory, and so.
Yep.
This becomes a go-to.
Exactly. So you have two integrals. You got them the wrong way around. Okay, so we're going to flip it into an integral over r. There's an e to the minus kx. This is an r. And then an integral over e to the minus u. And now I want to write, instead of a u to the s, I want to write this as u over x squared plus y squared. They don't depend on each other at all. Yeah, I just very artificially stuck in this this integral. They have nothing to do with each other. And then we reverse order. And the point is to sneak these two together, these s powers together.
You'll be able to free stuff.
Du over u, dx. For any fixed u, I can make a change of variables. For any fixed x, I can make a change of variables in u. U goes to u times x squared plus y squared.
Yeah, this is just.
That will kill this. It doesn't do anything here because of harm measure. It doesn't do anything on the range, but it puts an x squared plus y squared into the exponential. Okay.
It always like baffles me how powerful these like change of variables can be once you exchange. So it
Yep.
almost feels like there's some other hidden explanation for why this is true.
Uh-huh.
Yeah.
Okay. Is that so far so good?
Yes.
So all I did is I replaced u by ux squared plus y squared. And then I opened these two.
Right. And
Because
then
of the, and
Okay.
you don't get any du because it cancels.
It-
That's
this-
always
hard measure, right?
Yeah. No, it's trivial.
It's not trivial. I think it's very deep.
I mean, every time it happens.
I mean, it's like the specific instance is trivial, but the fact that you're using the outside variable in your inside change of variables is like wild.
If you were translation and just the x, we wouldn't ask this, but now
Yeah.
I haven't seen this.
So you see inside this integral, how do you split an x squared plus a y squared? There's no way to split these apart. There's no way to free them. How do you free the variables? You put them in here.
Use hard measure to your advantage.
Once they're in the exponent, now we free them.
Yeah.
Now there's a clean x squared with this y squared. This is a separate term. Now I want to reverse orders again.
Yeah.
Now that I've separated the x out from the y, now I reverse orders again. So now I have an integral from 0 to infinity, and e to the minus u y squared. Y is fixed. Y has always been fixed. It's only x that we're integrating though. There's this u to the s du over u. And inside is an integral over all of r, e to the minus u x squared,
We're gonna get that nice pie, right?
e of minus kx dx.
I mean, this is just,
Okay. Now, so this is the Fourier transform of this function, e to the minus ux squared. I don't know the Fourier transform of the function e to the minus ux squared. I do know the Fourier transform of the function e to the minus pi x squared. It's a Gaussian, and it's its own Fourier transform.
Change the variables again.
Change your variables. So let's change your variables. X goes to, let's see, I want to get rid of that u, and I want to replace it with a pi. Now it's just dx, so we will get a change of variables, and this is going to change. Okay. So again, we have, for any fixed u, I can make a change of variables inside x, u to the s. The integral is still over all of r. I have my e to the minus pi x squared, just like I like my Gaussians. There's an e to the minus k root pi over root u. X. And then instead of a dx, I have dx times root pi, bless you, which is just a constant, divided by root u. Bless you. du over u. So I divided by root u over u.
There's something strange. I know this might be like
Yeah.
a weird question, but is there anything strange that could happen around 0?
You mean when k is equal to 0?
Or for u being
Oh.
equal to 0? And
Yes.
being negative.
And x being negative. All of our change of variables so far have not,
I'm just looking at this k root pi over u, right? That 1
Yeah.
over u. And then we're also integrating.
yeah, but everything converges absolutely.
Yeah, I mean, like
So-
it has to work, right? Yeah.
Well, let's see what we get out of this. Let's see what we get out of this. So this is the Fourier transform of the Gaussian. I know what the Fourier transform of the Gaussian is. It's the Gaussian.
Mhm.
So this is e to the minus pi Fourier transform squared. So this is k root pi over u squared. And that's it. That's what I know about this integral. So now we're down to just one integral. Right? This is this Fourier coefficient of the Gaussian, which is just the Gaussian at that Fourier
I
coefficient.
can see why you want these pi's, because you want to get the functional equation.
That's-
That is also,
Yep, yeah.
Okay.
Which, so if k is 0, this is just 1,
right.
right? There's the root pi, let me pull all the way up out front. The root pi is not going to bother us. And now I have an e to the minus uy squared minus pi k squared, another pi, so pi squared, k squared over u. And then a u to the s minus a half du over u. Okay. Now all I want to do is balance. I have a u times something and a 1 over u times something. And I'd like those to be balanced. So I'm going to make a change of variables. U goes to u. I want to divide by 1y. And I want to multiply by a k pi.
Wait, you're making another function here, right? This has another name.
The K-Bessel function.
Oh, yeah, that's.
Yep.
Right, yeah, that's exactly what it is. Yeah, yeah.
Now, this is the one place where I have to be a little careful. There's a k squared. U has to be positive. So I have to take the absolute value of k.
Okay.
Okay. So I get my root pi factor, integral from 0 to infinity, e to the minus. U is replaced by, so I have a u absolute value of k pi over y here. No, and then a 1 over u.
Oh, right.
So minus, but it's the same thing,
Same fact.
k pi over y. So in fact, this k pi over y, I can pull out.
The Bessel function is defined with 2 around the Bessel level.
And I get a u plus 1 over u.
Yeah,
That's exactly what I want. Okay. Then u got replaced by these things. So there's a u to the minus s over 2 du over u, and a factor of k pi over y to the s minus a half.
Yeah, then you have pi to the minus a half, but then you have a pi to the 1/2.
Yep. And when I put the pi to the minus s in, to really complete everything, when I put a pi to the minus s in, the pi's are gone. It exactly cancels out all the pi's. Okay, so we're out of time, but let me just recap where we paused. We're almost through the calculation. Where we have paused is the following. So we took the Eisenstein series, the original Eisenstein series. We multiplied it by zeta of 2s. We multiplied it now by another thing, which is gamma of s. And why not? Let's multiply it by pi to the minus s. So this is the completed zeta function. And we took the Fourier expansion of this. So we said, let's write this as a sum over k, a k of y s, e to the kx. So I don't know, I put a star before or I didn't. I'm changing the definition by pre-multiplying by these things. Okay. The k equals 0 has two contributions. See, if k is equal to 0, then this is actually very easy to evaluate. Let's notice that, in fact, we should do it before we make a change of variables that destroys things. If k equals 0, what do I get here? I just get a gamma function, right? I can make a change of variables. Y goes to u goes to u over root y. That kills this and makes a nice gamma function. So I get gamma of s minus a half. And a factor of y to the, all right, I'm trying to rush this. This is just the gamma. We'll pick up here. Yep. This is a gamma. If not, then it's something else. So k equals 0, we have a couple of terms. We have this term c of s times y to the s, maybe with a factor of 2. There's another factor, which is the one that we found before, the zeta of 2s minus 1 times y to the s. Okay, so there's a second factor, which we'll work out in detail next time. Second factor, which will actually be the same factor with s replaced by, this is a 2s, with s replaced by 1 minus s. And if k is not equal to 0, what we found so far is this, 2y to the s, 2y to the s, this modular bit, which is a divisor sum, that divisor sum gets multiplied by k to the s minus k to the s minus a half sigma 1 minus 2s of k. And then, see, the Blackboard's better because you can see all these things at once and point to them without scrolling back and forth. And then this Archimedean thing that we, I killed the pi and the square root of pi and the pi to the s with a pi to the minus s. The k to the s minus a half I already noted. So all that's left is this factor of y to the s minus a half in the denominator. So this is a half minus s, which perfectly kills the y to the s. We just get a root y times this funny integral. So this funny integral is what we will discuss. Next time, it will turn out to be a K-Bessel function.
To the entire, right? And then, so it's not gonna contribute any folds.
We have to look at the analytic behavior of this thing.
Right.
So e to the minus k pi over y. Why do I have an over y? I should have a. The y is in the wrong place. Don't want an over y here. Anyway, we'll continue with this calculation next time, but we're very close, and then we're going to understand this expression. Okay, so this is the analytic continuation of the Eisen. Well, it's not yet the analytic continuation. At the moment, it's the just the Fourier expansion of the Eisenstein series.